All right, let's go on to variance. So we've been talking a lot about expectation, and these ideas, like, okay, dude, I know you're probably dying right now. It's so much algebra, super abstract, z's and x's and y's, and linearity and total expectation and whatever. But these things are super, super important. Um, and again, just zoom out to the big picture. We're just trying to ask about what is the population value of some population summary of some value, like an average, right? And often we're interested in transformations of those measurements, like if I take the log of a variable or whatnot, or combine multiple variables, how does that change what the population average is? So now we're going to build on that a little bit and talk about variance. So it's going to kind of be more of the same. I apologize, but we'll get through it. And you'll see how variance builds on expectation, and hopefully that will start to give you an idea of why expectation is so damn important, and why these rules, where you're thinking, why would I take the average of age plus height over 2? Or like, well, why would I ever do that concretely? You don't. But you use those rules that you learn for expectation to derive certain properties of variance and then properties of covariance, and those are things that we're going to use in pretty concrete ways. So let me show you what I mean. Variance. What is variance? It is the average square distance from the mean. So if I take, again, think of this as a mutate. If I take my population data that has a column x, right, and then I mutate that, whatever these values are, and then in this column, I have x minus expected value of x squared. There's going to be some other numbers in here, okay? Remember this expected value of x, that's just a constant. So I can first calculate what that is outside of the data frame. Like, you know, I can just take all of these numbers and I can calculate expected value of x. Let's say it's equal to 5, whatever. Well, then what I'm going to mutate to is x minus 5 squared, okay? Whatever that number is. So then I'm going to fill this in with all those numbers, and I'm going to take the expected value of that column. So here I'll just put this again more generically. Squared. Or sometimes you'll see this written x minus mu squared, where it's understood that mu is the expected value of x, or if it's not clear what variable it's the expected value of, maybe you'll put a little x down there. This is all just different ways that you may see that are writing the same thing. So why this transformation? What the hell is this? Well, x minus expected value of x, that's just a distance, right, from the mean. So let's say that you have on your number line, right, your mean population value is like 5, right? Let's say for a given person, the value that they actually have is 8. So x minus the mean of x is just the distance. How far away is this person from the mean? That's it. And the square is doing kind of two things. One is that it means that, so here's 8, and then here is 2. One is that it means that these two people, if it's 2 or 8, they're the same distance away from the mean, right? It's a distance of 3 either way. So we're making it so for the value of x equals 2 and the value of x equals 8, it doesn't matter if you're on the right of the mean or the left of the mean, you're the same distance away. And squaring it, because here this is minus x minus expected value of x. And so if you square it, then that minus sign goes away and it's all positive. So it gives you all positive numbers that you can compare as kind of like an absolute distance rather than to the right or distance to the left, which is signed. So it just gives you distance from the mean. The other thing it does is that since this is a function, the square function is, so let's say that whatever, let's say this is the mean here. Since this is increasing, the square function increases like this, right? It means that the further away you are from the mean, this kind of like distance measurement is penalizing you more and more. This is an increasing function. Increases faster than linearly. Okay. Why do we care about this? Let's dig into that a little bit more. So I think hopefully you understand what it is concretely, how you can calculate it. If you had a population data set, for example. So let's think a little bit about what this actually looks like concretely for some distributions. So here I'm showing you, let's just focus on the top. This is a Bernoulli distribution, which means it has mass 0 except at x equals 0 and at whatever the other value is. So here I'm actually shifting what that value is. So here is the pink line, which you actually can't see because it's behind this. It actually kind of goes like this. It's behind this black one. So here you have a random number that's either 0 or it's 1 with probability 1/2. And with the red line, I have a number that's either 0 or it's 2 with probability 1/2. And then this one is either 0 or 5 or something like that. And what I'm showing you is that those have different variances. Those distributions have different variance because the variance, again, is a population summary. Okay. For a random variable x, when you ask about what the variance of x is, that's going to be a number. It's a single number. It's asking how far away on average from the mean is this measurement in this population. So when you look at this Bernoulli distribution up here, for the pink lines, the mean will be somewhere in the middle, right? And so the distance to the mean will be about 1/2 for everyone, right? But if I say it's either 0 or 2, then the distance from the mean for any given person is increasing. Similarly for this one, the distance from the mean from most people is bigger. So it's kind of giving you an idea of the spread of this distribution, and you can see that perhaps more clearly in for these continuous distributions. So here we have a exponential distribution. So this is another one of these distributions that has a name. You may have seen it on the homework or something. And you can see if you set the variance of this distribution to be very low, it's kind of peaked. And so for variance equals 1, it's kind of peaked. And you see a lot of the mass of this distribution is near its mean. So the mean value is somewhere around here. A lot of the mass is near its mean, and then it goes to 0 pretty quickly. Whereas if you set the variance to be 25, there's a lot more mass that is further away in the tail. Really, it's the other way. It's the fact that there is mass in the tail that means that the variance is 25. I'm just kind of showing you examples. Similarly with the normal, if you have a low variance normal, most of the mass is near the mean. For a high variance normal, there's a lot more mass out in the tails. So that's some graphical intuition. If you want some physical intuition, similar to what we were talking about expectation, where it's the balance point, the variance is like rotational inertia. So it's the force required to spin the density around the mean. So if I stick a spit through this density kind of like this way, and I try to twirl it around, how hard do I need to push it? So some of you may have gone to the Exploratorium or science museums and things like that, and you know that if you get a bike wheel, right, and you spin it, it actually takes some effort to, if let's say it's spinning around this way, you're holding it like this, and the axle is spinning like this, it takes some effort to rotate it. You may also know that if you have bike or motorcycle, you can actually feel it. It'll resist you. And the question is just how much force do you need to put in to get it to spin? So if you have a lot of mass spinning around the outside of the wheel, it's going to be hard to get that going. It's hard to get that to accelerate. If your wheels are very small, then or all the weight is in the middle, like if you Google time trial bikes for the Tour de France and stuff like that, you'll notice, well, one, the wheels are covered, so there's no spokes. It's like a solid mass. But two, actually a lot of the mass is in the middle of the near the axle, so that they can accelerate more quickly. So, for example, if you had something like this with all the mass near the center, it'd be kind of easier to spin it than if you had something like this. You'd need people pushing on further out with the same amount of force to get it to spin, or a larger amount of force the same distance out. And if you had it like that, this would be very difficult to get going to start spinning. All right. So why do we care? Let's zoom out again. Why would you want to know the variance of some health related measurement? So let's talk about, like, I don't know, the variance of HbA1c measurements. So it's like a blood sugar measurement, often taken for people who are diabetic. Why would we want to know in a population of people, let's say, like, people in California, what's the variance of HbA1c? There's a lot of reasons, but one obvious one is if it's very low variance, then that tells you that everyone in your population has roughly the same value, and there's some homogeneity. Whereas if it's high variance, you might think, well, there's some people who already have very well controlled blood sugar and others that are not, right? So what's the difference? It might lead you to ask, what's the difference between these people? Why are some people uncontrolled and some people are controlled? And let's dig into that. Let's figure it out. Whereas if it's everyone's the same, then maybe it's more of a one-size-fits-all kind of solution, or maybe there's no problem, right? So this is a very basic, broad kind of question. I'm just trying to motivate why variance is a population quantity at all that we would care about, because it's easy to think about why would we care about the mean, but why would we care about the variance? That's also sometimes important as a thing that you would want to know in its own right. But we'll also see that variance is also just like an incredibly useful tool thinking about estimation problems in the future. Okay, so how do we do it mechanically if we have sampling? Well, if you draw some values of a random variable, if you want the variance of it, just very brute force, take x, subtract off the mean of x, square that, take the mean of that. You can do that. You could also have, if x were in a data frame, you could do this with a mutate and then create a new variable z, like I showed you a few slides ago, and then take the mean of that. But if you want to skip all that too, you can just use this var function in R, and these two things give you exactly the same answer. So var is literally exactly this. Okay, so I showed you this definition up here, but there's a completely equivalent definition. This one is often easier to work with in terms of when you're doing algebra or derivations. This is usually the better thing to use. And it's exactly the same. So prove it. Again, this is just a kind of algebra exercise. I do encourage you to try it. Even if you haven't done algebra in a while, just bone up your skills a little bit. It's good practice. So here, it's just so I'm going to write mu here for this. Just so that it doesn't take up so much space. So this is x minus mu squared is this term here, which is, I have the expectation of that. Okay, so I'm just going to multiply. So that's the x squared minus 2x mu plus mu squared. And now, linearity of expectation. Remember, this mu is just a number, it comes out. And then the expected value of a constant, I can take that out. Or you could think that the expected value of a constant is just a constant. Either way you want to look at it. And yeah, okay, great. Now, what is this term? So by my definition, this is just mu, right? So we have a minus 2 mu squared plus mu squared gives us minus mu. And minus mu squared, which is exactly what we have here. This term is this, and then this term is this, my minus mu squared. So it's just like 2 lines of algebra, right? That's it. Nothing fancy. All right. Let's look at this. I think this example we did, let's just approximate the variance for each random variable. Done. Okay? Not too difficult. Again, the point of this is just mechanically and to understand what's happening. And you could also show you're going to get the same thing if you do this. Same thing. Okay. So like expectation, you don't have to do this for common distributions. It is known based on the parameterization, the parameters of the distribution. We know what the variance is, just like we know what the expectation is based on this parameterization. And if you want to derive these the way I derived the other thing, again, it's the same math. You just literally use the formula. You put the density in there, and then you start plugging and chugging. Because variance is just a special expectation. Variance of a variable is just the expectation of this transformation of that variable. And so you just use the formula for expectation, given that you know that what the density is. And all of these things you can drive. So if you want to see that, that's super easy for ChatGPT to do. You can also just Google like derivation of variance of normal distribution or something like that. You'll just see it's straightforward algebra. So these are the maybe let's do this one because it's kind of instructive. This one here. So let's start from the definition a definition of variance, right? So let's use the second definition that we just saw. So it's the expected value of x squared minus the expected value of x squared. So there's a difference, right? This is not the same as that. This is the expected value of x squared. This one is x squared. So you take each, show it like this. So here's x in your data frame. Here's a mutate to get to x squared, right? So if this is little x, then this is going to be little x squared. So for example, like if this is 2, then we're going to be a 4 here, right? And then you can take this column and take the expectation, the population average, right? That is the expected value of x. And then I can choose to square it, right? And that's what I get. So this one is first you square x, and then you take the population average of that, which gives you this expected value of x squared. Okay, so it matters. It matters what order you do it in. Okay, so let's go back here. So let's just compute these things. So x is a Bernoulli random variable. That means that the density, I get x equals 0 with probability 1 minus p, and x equals 1 with probability p. That's the density function. Again, plot-wise, you can have at 0 and at 1. Here we have probability p. And then here we have, this is 1, 1 minus p. Okay, so that's my density function. And we can just compute these expectations using the definition of expectation based on the density function. So let's look at this one. Okay, so this is my g of x. G of x. So this is the expectation of a function of a random variable. And you can see that when x equals 0, it's going to be 0. So this is just f of 1, which is p, times 1 squared, which is 1. And then the other term, well, we already know the expected value of a Bernoulli random variable with probability p is p. So this is p, and then we just apply the square. So in total, we have a p minus a p squared, or I can bring a p out, and that's p 1 minus p. Okay, that's it. So what's kind of cute about this is that you have the probability of it. It's the product of two probabilities, the probability of it being 1 and the probability of it being 0, because this is what's left over, the probability that's left over if it's not 1. So hopefully that's illustrative a little bit of how these things are actually calculated. It's not really that important for you to do those calculations, just kind of know what the idea is. Okay, there's also this concept called standard deviation. What is standard deviation? It's just the square root of the variance. So this is again, remember, it's a population idea. So in the population, a particular measurement has a particular variance. And by the way, this notation, that's what it means. This is, what is the variance of this measurement in my population? The standard deviation, which nobody ever writes like this, but you can. If you say like SD of this measurement, it's just what's the variance of that, and then take the square root of it. That's it. So the reason that people talk about standard deviation instead of variance sometimes is because the standard deviation has the same units as the variable of interest. So you can talk about when I was talking about the right, this is like the distance. This is kind of like a distance squared, and then we're averaging the distance squared. Well, so this is kind of like an average squared distance. So if I want like an average distance, like how far away are people away from the mean on average, I take the square root of that. And this is going to be on the same scale, the same units. Like if x is measured in inches, then the standard deviation is going to be a number of inches, whereas the variance is going to be a number of inches squared. Okay. But it's really not like a big difference, variance, standard deviation. I mean, obviously they're different numbers, but it's just like, if I tell you one, you have the other. You just have a square or take the square root. It's not a big deal. Okay, so we talked about the linearity of expectation. Variance is not linear, okay? Variance works a different way. And the variance of we alluded to this in an earlier video. When you scale a random variable and you ask about the variance of it, it's not going to be it's going to scale with the square of that variance. And we talked about this a little bit, right? So if you have your original distribution, let's say f of x, right? How is that going to change if you multiply x times some constant, right? So you have to imagine, like, let's take all these people here. They're now going to all end up here, right? And then you take all these people here. Where are they going to go? They're all going to end up here, right? So this is an example where I'm actually shrinking it. I'm scaling it down. All these people are going to go here. So I'm scaling it down. You can also have examples where you scale it up, and that's what we saw before. So scaling, multiplying by some constant to a distribution is actually going to expand or contract that distribution, generally speaking. And so you can either expand it or you can contract it. And it turns out that what changes linearly is the standard deviation, because again, we're measuring here distance squared with the variance. So the standard deviation is scales with a, the same amount, but for the variance, you actually get another factor of a out. So this is a concrete example. So if you have a equals 2, and here I'm taking 1 million samples from a standard normal distribution, and then I'm mutating, or just generating another column that's equal to a times that standard normal, and then I ask, what's the variance of both of those? You'll see the variance of the original one is 1. Okay, cool, I knew that. The variance of the other one is 4, which is 2 squared. And that's what this formula is saying. So you can pull the a out, but you got to square it. And this is, again, I'm not going to drive this for you, but it's very straightforward, follows from linearity of expectation. So if you just do kind of like the derivation that we did here, and you put in ax, and then you just crunch through everything, you're going to see exactly that you get an a squared variance of x. All right, so quick check. If I know the variance of x, what's the variance of minus x? So there's an intuitive answer and there's the kind of mechanical answer. Intuitively, you can just think about the density function of x and the variance as some sort of measure of the spread of that density. If I ask about the minus x, all I'm doing with that density is I'm flipping it and whatever, or you could think of changing the axes. So if my x-axis was positive this way, negative that way, I flip the axis, but the density stays the same. So that density object is the same. Like if I cut it out on a piece of paper, that density is the same density, whether I flip the axis one way or another. It's just kind of be in a different place on those axes. And so the kind of overall spread of it, or how hard is this thing to rotate, that's not going to change. So it should be the same. Okay, so that's the intuitive way to think about it. The mechanical way to think about it is to apply what we just learned. And by the way, it's kind of like a meta picture. I think it's really useful to do both of these things simultaneously. Like always try to be going back and forth between your intuitive understanding of something and the mechanical understanding. Because sometimes your intuition is wrong, and if you can't check it mechanically, then like you're just gonna you can check if you're being an idiot if you can do it mechanically. But also if you're doing it, sometimes your intuition isn't quite developed enough, and by doing things mechanically, it can let you see things, right? You just kind of apply brute force a couple of algebraic operations, and you get somewhere, and you look at that, and you're like, oh, I see what happened there, right? And so your kind of mechanistic, rule-based understanding and your intuition, like physical or otherwise, can synergize with each other and serve to build upon each other, rather than being like completely alternative modes of thinking. So mechanically, the variance of negative x, I can write as the variance of minus 1 times x. And now I can take that minus 1 out, but I got to square it. And now you see very obviously this is just 1. So that is the variance of x, and we're done. Okay. Is this true? Variance of x plus y, is that equal to the variance of x plus the variance of y? So I'm telling you it's not. Okay. And can you prove it? It's just algebra. So here I'm going to use the formula or definition, I should say, that it's the expected value of this thing all squared minus the expected value of that thing squared on the outside. So when you do, if you multiply these out, you're going to get over here an expected value of x squared plus an expected value of 2xy plus an expected value of y squared. And then this term, you have minus, so let's just bracket, minus, so linearity of expectation, this is equal to the sum of the expectations. So we have e of x, and then you squaring that sum of expectations. And you get this. Is this equal to the variance of x plus the variance of y? No. And the reason I know that is because I can see that this term here plus, well, minus this term. So these are all subtracted off from this. This is the variance of x, right? That's the definition of the variance of x. And now you may recognize that this term minus that term, that is equal to the variance of y. So we're close, but the problem is that we have this extra stuff in here, right? we actually also have this other term, which is 2 times the expected value of xy minus expected value of x, expected value of y. Okay, so unless this thing is 0, then this is not true. Okay, so question for you, when is it that this is 0? How can we get this to be 0? Well, if you remember about independence, if x and y are independent, this expectation factors, and these two things are equal. So then if we subtract them, they're equal. So actually this is true, but only for independent random variables. If x and y are not independent, it is not true. So that's kind of interesting. Or it is not true in general, but if they are independent, you can prove that it is true. So now let's do a little simulation. I'll show you that that is indeed the case. So we don't actually need to even do anything new. Let's just do it right here. Let's calculate some stuff. So here I have a situation where y and z don't appear to be independent. And so let's calculate some stuff. So I want to calculate the variance of y, the variance of z, and the variance of y plus z. Forgot a comma. Okay, so this plus this is not that. You see, we're actually getting something that's more than the sum of these two things. In this case, it seems. So we have like an extra like 2/3 coming in there somehow, and that's exactly the contribution of that extra term, which in this case ends up being positive, but in general it doesn't have to. That extra term doesn't have to be. And let me illustrate the other case that we saw. So we know that x and y are independent in this simulation. So let's leave that as y, but change this to x. And look at that. The sum of these is indeed that.